kind of stuffed up this week. That's okay. We can still get through what we need. Sorry it's taken me so long to get this to you, but we're looking at wavelength, Nearfield, and half angle beam spread. Alright, the stuff that you might have gotten already might be a little bit different than that, but that's okay. You might have seen a little bit different form of this equation, but that's no problem. Just trying to make sure my phone's turned off there. Anyway, wavelength, near field, beam spread. So basically, if we have a wave here, compressional wave or a shear wave or whatever, we're trying to measure the distance between these points. Okay? Relatively simple calculation. All we really care about is velocity of the material, frequency that we're dealing with. Let's just make it easy. Let's just say we have a velocity of 230,000 inches per second coming right off your data sheet there, and a frequency of 5 megahertz. Okay? So we'll say this is steel, and this is 5 megahertz. So let me grab a calculator real quick. Alright, so we've got our information there. 230,000 divided by 5 million equals 0.046 inches. And from what you've read already, you can tell that if you're looking for a defect, that defect needs to be at least half the wavelength. So that's going to be 0.23 or 23 thousandths, meaning in order to see that defect for that setup, it has to be at least 23 thousandths of an inch wide to pick it up. Okay? Relatively simple. The next one, near field, is along that same line. We're going to stick with these same numbers here. Steel 5 megahertz, and we need a diameter of a transducer, so let's make it easy. Let's say it's 1/2 inch. Okay? So we're just going to take these numbers, okay, these numbers here, and just plug them into this formula. It's really not that bad. So 0.5 squared times frequency over 4 times velocity, that same velocity, 230,000. And I'll just work this out a couple ways here. 0.5 squared, whoops, push the right buttons, 0.5 squared times 5 million equals 1,250,000. Alright, and that's going to be over 4 times 230. That's 920,000. Okay? Divide those out. 1,250,000 divided by that. That tells me this near field 1.35 inches long. Okay? Now the beam spread. We're just working the formulas, and then I'm going to draw a picture and show you what this is all about. So if we have this here, let me get rid of that. We're still keeping these same numbers, just plugging them in. 230,000 diameter. There's our diameter. Frequency, 5 million. What's that going to tell us here? We have 230,000 divided by 0.5. Whoops, let me get a couple parentheses in there. Times 5 million. That's going to equal 0.092. But that tells us we've done this right here. Okay, we've done all this with that right there. We still have to do this and this. Okay? So multiply by 1.22. Let me get out of the way here so you can see. We did that. We still need to do these two. Okay? So here's our setup for this. multiply, divide, got 0.092 for all that, multiply by 1.22 right there. I come up with 0.1124. Now we've got sine of the angle equals, all the way over there, 0.1124. So now we need the inverse sine. So on my calculator here, I push sine, or shift sine, and then type in that answer, and I come up with a total of 6.44 degrees. But I kept all my decimals. So if you worked that and didn't keep all your decimals, you might come up with something a little bit different. Okay? Relatively simple. Wavelength, near field, beam spread. And really all that means is this. Here's your transducer. Comes down, kind of cones in, cones back out. Inside of here, all of this area where the waves are all inconsistent, that's a near field. Okay, meaning all the waves are in there, they haven't really done anything for us yet, they're not really doing anything, there's constructive and destructive forces happening in there, and that's just going to tell us that once they've completed that near field and got their uniform wavefront, all of this down here now is the far field. And this, if we were actually measuring, would be where our beam spread comes from. So we would just measure this angle. That would be 6.4 degrees. This over here again would be 6.4 degrees. So all together there, that looks to be about 12.88 degrees total beam spread. Okay, and that's just going to continue to cone out as it stretches out into the material. So, near field, relatively simple. Far field, again, relatively simple. That's just where we can do our inspection. There's our beam spread of 12.8 degrees, almost 12.9, and really, that's all there is to it. That's just how it is. So, wavelength, near field, beam spread. Relatively simple calculations, it's just plugging in the numbers. Any questions? As always, feel free to email me.